You might be wondering how these capacitors are made. In other words, what would it look like if I could take one of these capacitors apart? I'm not exactly sure what I'm going to find inside of either of these. I'm going to guess it would be something similar to this capacitor. So this one, you can take the top off, and when you get inside, it's actually really simple. All it is a big rolled up piece of a conductor with a back layer that's insulating, so when it's wound around, there's an outer and inner layer, and by winding it up several times, you really create a very large surface area across which you can store the electrical charge. So you can make your own capacitor like this if you just had a big sheet of aluminum foil and then you backed it with paper and rolled it up. So this is how all capacitors are made. Generally speaking, any capacitor is made out of two conductors separated by one layer of insulating material. So the most common, no, not the most common, the simplest form of capacitor is called a parallel plate capacitor, and this is exactly what it sounds like. The two conductors are metal plates that sit parallel to one another, and then there's some layer of insulating material. In this case, it's cardboard between the two. And sometimes you have air-filled parallel plate capacitors. The air in the space between is itself an insulating layer. Okay? So that's the simplest of all. Two pieces of metal separated by air, an air-filled parallel plate capacitor. Another type would be something known as a Laden jar. I believe that's how it's pronounced. Perhaps it's Leyden jar. So I have an example of the Laden jar or Leyden jar right here. One conductor, a second conductor, and in this case, separated by an insulating material made out of glass. I don't have an example of this, but I'd imagine you could make a capacitor in a spherical shape. So you could have a spherical shell with a tiny hole in it so that you can make contact with a wire to an inner solid metal conductor. And the layer doesn't have to be air, it doesn't have to be glass. You could fill this up with oil. In fact, I've seen oil-filled capacitors before. This device is a variable capacitor. By turning this knob, you can see that it's kind of like this parallel plate capacitor, but it's got several layers to it. And as you rotate the knob, right now this would be zero capacitance, and then once they become fully parallel to one another, you get the maximum capacitance. So you could vary the capacitance by rotating the plates in and out of alignment. So there are several layers of these metal plates, and as I rotate the dial, I go from zero capacitance to maximum capacitance. These are this knob really effectively would be like the tuner knob on a radio, right? By adjusting capacitance, we'll learn later in this semester that you can change the resonant frequency of an electrical system. So here's another example of one of these variable capacitors, and you can see the multiple layers, but instead of air being the insulating material, this is all filled with an oil, okay? So then we have, again, the air-filled parallel plate capacitor. Unfortunately, I can't give you the full demonstration I'd like to. What I want to show you is that with a meter that measures capacitance, the geometry of the capacitor can be shown to affect the capacitance. However, my meter's broken. So I'll tell you what should happen. The distance between the plates has an effect on the capacitance as well as the surface area. There's an equation for this. For a parallel plate capacitor, the capacitance is equal to the permittivity of free space multiplied by the surface area of the metal plates and divided by the distance between the two. So if our metal plates are separated by a distance d and have a surface area of a, there we have it. Actually, I should get rid of this subscript. Epsilon with the subscript 0, we call epsilon naught, represents the permittivity of air, but I can take other materials and put it between the plates. For example, the cardboard could go in here, and that would increase the capacitance. I could fill it with a different insulating material, in this case, like a rubber sheet, and that'll also increase the capacitance in a different way. So instead of the permittivity of free space, it becomes the permittivity of whatever this material happens to be. So I say these things are insulators. They're often referred to that layer of insulating material as a dielectric layer or a dielectric material. Okay, so a conductor, a dielectric, and another conductor. And if it's a parallel plate, the capacitance is inversely proportional to the distance between. So what I'd like to show you is that I can slightly adjust this one and move the plates closer together. And in doing so, the reading on the meter would go up if this was operating correctly, and I slide it farther apart and the reading goes down. I can slide it to where the spacing is just big enough to insert this material. And you see with this material halfway inserted, the capacitance would go up a little bit. With it inserted more, the capacitor goes up even further, and eventually, with it all the way in there, the capacitance goes up as high as it can. Now, we could actually unscrew these and take the two plates and face them this way. So, with the capacitors here, I have full capacitance, but if I move the plates like this, there's still a non-zero amount of capacitance, and then with the plates sitting in this orientation, again, if I take some dielectric material and put it here, the capacitance would go up. Well, this is how a stud finder works. So if you've ever swiped one of those devices across the drywall to figure out where the studs are in the framing of your house, you're really just taking a capacitor where the plates are faced this way, and you're sliding it around, and when the material here is all gypsum board or drywall, it registers a certain amount of capacitance, but as soon as it changes from being drywall to a wooden stud, the capacitance goes up and the stud finder starts to beep. Pretty neat.